So, in previous classes we have looked at thermodynamics, fluid equations, and then to a particular assumption, quasi 1D assumption, where we consider that the properties of the flow like velocity, pressure, density, temperature, they remain constant across the cross section of the flow. So, that is a quasi 1D assumption, and then we had looked at conservation equations in the quasi 1D framework. Now, let us apply some of these principles to first look at a very important characteristic of compressible flows, that is the speed of sound. So, sound waves are very important when discussing compressible fluid flow, as we had discussed in previous classes, including the flow regimes, where it is the main mode of information transfer among different parts of the flow. So, you have when we have low speed flows or subsonic flows, then these waves can travel all around carrying the information, but once the velocity of the flow becomes greater than velocity of sound, the information propagates only along certain directions. So, now speed of sound being so important, let us analyze the sound wave using 1D principles that we had just completed. So, this wavy line represents the wavefront of the sound as it is travelling from right to left. So, when as it is travelling to from right to left. Now, in order to apply this, we use the principle that if the body is moving, or these waves are moving with uniform velocity, it is having a certain velocity a, then you can always transform the coordinates or transform and impose an opposite velocity in order to make the flow or make the wavefront stationary. So, you can give a velocity a now that appears going from left to right. If you impose that, then this wavefront can be made stationary, and then the steady flow equations can be applied on this wavefront. So, the equations for now, this is a section which is a in one dimension. So, you consider the one dimensional flow where you have rho u a is constant. Since a is constant, you get rho u is constant. The u is the uniform velocity, and p plus rho u square is constant. This is from momentum conservation. There is no heat addition or work done in these processes. So, you get h plus u square by 2 is constant, that is conservation of energy. So, using these three principles, let us look at how we can get to the speed of sound. Now, as the wave passes over as the sound, it introduces a small change in the local static pressures, temperatures, and densities, as well as the speed. So, that small change is represented by delta p, delta rho, delta t, and the small change delta a. Now, we apply these conservation equations across the disturbance. So, if you write the mass conservation equation, you get that rho a is equal to rho plus d rho multiplied by a plus dA. It is just the conservation of mass. This can be expanded and you apply the condition that when you have two small quantities d rho and dA getting multiplied, these are approximately equal to 0, they are negligible. So this when expanded you get rho a d rho plus rho dA plus dA d rho. Now this factor is negligibly small, so it can be removed, while these two get cancelled from here. So you get the equation a d rho is equal to minus rho dA, or A can be written as minus rho dA by d rho. So we have from the mass conservation equation we get this particular form of the equation, or this particular formulation. This will be useful ahead. Now we consider the momentum conservation across the wavefront. Okay. So when you look at momentum consideration, you have p plus rho a square is equal to p plus dp plus rho plus d rho multiplied by a plus dA the whole square. Okay. So now here you have to expand this formulation, or this right hand side, and in that the terms dA square is very small. Similarly d rho dA, they are also very small and you can neglect them. So you get p plus rho a square is p plus dp plus rho a square plus 2a rho dA plus a square d rho, and you can also, so from these terms this gets cancelled, similarly this gets cancelled, and you can use the equation here that A is equal to minus rho dA by d rho, and that can be substituted here, and when you substitute that equation, then you will get a square is equal to dp by d rho. So when you combine these two equations, what you get is that all these terms, that is due to dA square 2a d rho dA, they are all very small and they can be neglected, and you can use the term that you got from the previous equation, that a d rho equal to minus rho dA. So this is the equation, or this is the term that we got from the previous equation, and that can be applied over here. There is a rho dA term here, and it can be replaced by a d rho, and there will be a negative sign, so that this equation then forms minus a square d rho plus 2a square d rho plus a square d rho, and you have a dp term here. So this is how you get that's equal to 0. So you get a square d rho equal to dp, or a square equal to dp by d rho. So once you get this, so that this relates the speed of sound to the gradient or to the derivative of pressure dp by d rho. Now in order to evaluate the speed of sound, you should evaluate this derivative dp by d rho, but we know that we should determine the process by which the sound is actually traveling, or the thermodynamic process involved in the speed of sound. So now that one needs to determine the process, when researchers were looking at it right from Newton, he sort of said that sound wave propagates in air, and when it propagates it does not change things to a great extent, and so he assumed that the temperature remains constant as the sound waves propagate through any medium. So he said that it is an isothermal process. So if you consider an isothermal process, then the corresponding thermodynamic equation is PV equal to constant. This can be differentiated, PdV plus VdP equal to 0. In terms of density, it will be dV is V is just 1 by rho. You can substitute that, and you can get dP by d rho is nothing but P by rho, or you get A square is equal to P by rho. But it was seen that this was not correct according to experiments. There was a discrepancy with experiments, and correction was provided later in a sense that since these processes are extremely fast, it moves quite fast, there cannot be any exchange of heat. In order to have an isothermal process, you need to exchange heat, and the heat exchange is generally a slow process. So but speed with which sound travels is quite fast, and there is no time for such heat exchange to take place. So then the appropriate thermodynamic process is a reversible adiabatic process, or that is an isentropic process. When you consider an isentropic process, then the relevant equation is Pb power gamma equal to constant, and then if you differentiate this and get to dP by d rho, it is dP by d rho is gamma P by rho, or A square is gamma P by rho. And if you can also couple this with the equation of state, P is equal to rho RT, then you get A square is equal to gamma RT. So now here we come to the equation A is equal to square root of gamma RT. Now remember, in all these conversions we have assumed that the gas is a perfect gas, and only in the case of perfect gases we can use these kind of simplifications, where we are saying gamma is Cp by Cv and so on. But the most general equation is actually A square is dou P by dou rho, or at constant entropy. Entropy is equal to constant. So that is the correct thermodynamic process to be used, and when you use that, then this is the most general formulation for speed of sound. This is applicable in any scenario, while in specific to perfect gases you can simplify this to square root of gamma RT. Another equivalent formulation is using, it is gamma P by rho, square root of gamma P by rho. So we have done a bit of computation or a simple analysis to understand how the speed of sound varies with the temperature and what is a relevant equation to be used. This is in a context of changes of Cp and Cv as temperature increases to higher values, and you can and these are all plotted, and there is a comparison between using the formula A is equal to square root of gamma RT and determining A by square root of this generic formulation, that is at entropy equal to constant. This is done using computational tools, and here you can see the plots, and while for perfect gases, which is represented by the blue line, which is perfect all through, there is no difference between gamma RT and dP by d rho. But when you bring in high temperature effects and there is other changes like chemical reactions happening, then it can depart from such perfect behavior, and that departure is seen by these other lines. There is a difference between gamma RT and dP by d rho. So depending on the situation and the problem under consideration, while in majority of the cases that we do here, we will be dealing with perfect gases, and this formulation holds good. But if situations arises, then we have to go back to the more fundamental equation, which is this one, which is the square root of dou p by dou rho at constant entropy. Now speed of sound is not just in gaseous medium, it is also for solids and liquids, and there the relevant property is the bulk modulus, basically how changes of density with pressure, that is what is the relevant property. So the speed of sound is related to the bulk modulus and the density. So square root of bulk modulus by density, and you can see that for solids it will be very high, the speed of sound can be very high for 4000 meters per second in steel, while for water it is about 1.5 kilometers or 1500, close to 1500 meters per second in water. While for air at normal temperatures the speed of sound is around 347 meters per second. So let us just do a simple numerical based on the speed of sound. So here calculate the percentage change in speed of sound at 11 kilometer altitude when compared to sea level. Ambient temperatures are 288 Kelvin and 216.5 Kelvin at sea level and at 11 kilometer altitude respectively. So if an aircraft flies at 333.3 meter per second, what happens to its Mach number as the altitude changes, as it gains in altitude. So let us look at this. So what is given here? So this is air. So air has gamma is 1.4 and generally R is taken as 287 joules per kg Kelvin, and you have this at sea level and at 11 kilometers altitude. Temperature is given at sea level is 288 Kelvin, here it is 216.5 Kelvin, and the relevant formula is gamma RT. So one can find the speed of sound here. So A is in this case, first case, which is 288 Kelvin, this is square root of 1.4 this is 340.17 meter per second, while at this case at 11 kilometers this is the same formula. You have to substitute T as 216.5 and you will get 294.94 meter per second. So what happens to Mach number? Mach number is V by A, and now you can see that in this case the Mach number is 333 0.3 divided by 340, which is close to 0.98, while on this side at 11 kilometers, the Mach number, you can see that the speed with which the aircraft flies is greater than the speed of sound, and that is the Mach number here is 1.13. Now the percentage change in speed of sound as there is an increase in the altitude from 11 kilometer to 11 kilometers is 294 minus 340.17 divided by 340.17, and this is change is about 13.3%. There is a 13.3% decrease in the speed of sound. So as the flight moves to higher altitudes, temperatures drop, and there is a possibility that the Mach number of the flight can change. So with this we end the discussion on speed of sound. We can now look at few numerical examples in the next class, and that is the end of this class.